Yesterday, we were talking about slant asymptotes. We did an example where the slant asymptote was found by doing the long division between the polynomial on top and the polynomial on the bottom. Okay, and the quotient is what ends up being that slant asymptote. And we talked yesterday. The initial remark was when these differ by 1, when your leading terms differ by 1 in regards to their degree, you're going to have a slant asymptote, which is linear. Okay, but if they differ here by degree 2. So I want to show you what happens when they differ by 2. What do you think your asymptote is going to? It's going to be oblique, and it's going to be a power of 2. So your oblique asymptote is actually going to be a parabola. Okay? And some graphs, just depending on what the numerator is, what the denominator is, some graphs are going to, kind of hug that parabola more than others will. Okay? And we'll kind of see that in this example. And then we'll mess around if we have time with, maybe we can alter this rational function a little bit to see how that then impacts what the graph does around the oblique asymptote. But this question, about 90% of it is practicing what we've already done in a lot of these problems. Finding vertical asymptotes, see if there's holes, see if we have x-intercepts, see if we have y-intercepts, see if we cross a horizontal asymptote. The only difference is what do we do with the horizontal slant or oblique asymptote. Okay, so the one thing that on questions like this would be like the polynomial or the rational function that we start with. And the polynomial on top would be, I want to say, a nightmare to factor, but it's going to take us 4, 5, 6, 7 minutes to factor that because we have to use the rational root theorem. Okay, the P over Q stuff. And that can be time consuming, right? So in the event that happens, one, we're either going to have to do it, or I will provide you with some tools that kind of help maybe get the ball rolling. I might give you this and say, hey, 3 is a factor. Or I might give this to, or 3 is a 0. I might give you this and say, hey, 3 is a 0 and x plus 2 is a factor. Does that kind of make sense? And allow you to get the ball rolling with the division so that you can factor this top to x minus 3, x plus 2, x minus 1, x plus 5. Okay? The bottom, we should have no problem factoring. That's just a traditional quadratic, x minus 2, x plus 6. Okay, so these two things are the same thing. Is that okay with everybody? All right. I want to go through, so we know, looking at these, that the leading degrees are different exponents. The leading degrees are different exponents. Therefore, and the top one is bigger, you're not going to have a horizontal asymptote. You could have a slant or an oblique, okay? And because they differ by 2, you're not going to have a slant. You're going to have an oblique, okay? And I want to stop there. I don't want to go any further with actually finding out what that oblique asymptote is. I want to go through the easier things right now. I want to go through what is my vertical asymptote, what are the holes, what are the x-intercepts, y-intercepts, and then we'll come back and the bulk of the problem, the time that we spend on it, will be locating that oblique asymptote. Okay, so if I want to find vertical asymptotes, where do vertical asymptotes exist? Okay, so the denominator is going to be where we have discontinuity, right? It's division by 0. So we look for vertical asymptotes there, and we think right away there should be a vertical asymptote at x equals, from this first factor, x equals 2, and from the second factor, x equals negative 6, right? Okay. Now, were any of those common to the numerator? Was there an x minus 2 in the numerator? Nope. Was there an x plus 6 in the numerator? Nope. Okay. So that's the way I always start off. I always take the denominator and say, okay, everywhere I see a 0 in the denominator, I'm going to initially say that it's a vertical asymptote. And then I get to the holes question. I say, okay, are there any common factors? And basically allow me to distinguish whether any of those things I thought were vertical asymptotes should actually be holes. In this case, there are no common factors, so there are no holes, right? X-intercepts. What do I set equal to 0 to find x-intercepts? The numerator. So that thing right there gives me my x-intercepts. So 3, 0, negative 2, 0, 1, 0, negative 5, 0.
Pardon the interruption. Any sophomores who have not received their computer, please meet Mr. Jesko outside of Mr. Wilkerson's room. Again, any sophomores who have not received their computer. Thank you.
All right, so is everybody okay with that? Vertical asymptotes, holes, x-intercepts. Okay, where do I find y-intercepts, or how do I find y-intercepts? Set x equals 0. So you got two places you can do this. You can make x be 0 in all of these in the reduced version, or the factored version. Okay, or I can do it down here. I like to do it down here because those just disappear, right? And all you're left with is 30 over negative 12. And that reduces to negative 2.5. So being able to generate that information is great, okay? But just that information is going to, or only having that information is going to be problematic for the overall problem. I still need to know this oblique asymptote here. Okay, I still need to know that. So what we're going to do is we're going to find the oblique asymptote. And this is because I know that these exponents here differ by 2. The top is bigger. We are going to do the long division. So I'm going to take x to the 4th plus 3x cubed minus 15x squared minus 19x plus 30 and divide that by x squared plus 4x minus 12. All right, so we're going to ask ourselves, what do we put right here? Remember when we do long division, we're either asking ourselves, if I take x to the 4th and divide it by x squared, what is that quotient? Or what can I multiply by x squared to get x to the 4th? We all agree that that should be x squared? So now I'm going to distribute that. So we get x to the 4th plus 4x cubed minus 12x squared. Okay. And if you remember, I like to multiply everything by a negative. And then I'll just add straight down. So those go away. Gives me negative x cubed. And then add straight down here, it gives me negative 3x squared. And then minus 19x. And then plus 30. The next question is then, okay, how many times does x squared go into negative x cubed? Or what do I need to multiply x squared by to get negative x cubed? It should be negative x, right? So multiply that out, then I get negative x cubed minus 4x squared plus 12x. And I'm going to change the signs. And I'll add straight down. So x cubes cancel. Leaves me x squared minus 31x plus 30. And then what do I multiply by x squared to get this x squared? Positive 1, right? And that gives me x squared plus 4x minus 12. Change everything to its opposite. Cancels out. Gives me negative 35x plus 42. So this becomes plus my remainder over my quotient. Not my quotient, my divisor, sorry. Okay? Now, that's the long division. We've done that multiple times in other areas. Okay? Now, the idea here then is if I were to take everything that I have on top of this division symbol, take that whole thing and multiply it by the divisor out here, it should get me back to what is underneath the division sign, right? It should get me back to that x to the fourth plus 3x cubed minus 15x squared minus 19x plus 30. Okay? So, so basically what we're doing here is the oblique asymptote takes place of the horizontal or slant asymptote. And those two things, we were only interested in them because they told us what our function did when x got really, really big. So if x gets really, really, really big, think about what happens to that amount right there. If x is really, 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 really big, let's say x is like 1 billion, okay, which is 9 zeros, right? You'd have 35 followed by 9 zeros and add 42 to that and it'd be negative, okay? But on the bottom then, you would have 1 billion squared. Well, 1 billion squared is going to be 18 zeros, isn't it? Is that a very large number? Even though there's 9 zeros up top, is 18 zeros so much bigger? Yeah. So what is that remainder over my divisor? What is that thing going to go to in regards to x becoming really, 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 really big? 0. That thing is not important to us in regards to the end behavior. Okay? So, what's that mean to us? That means this thing right here tells us what our end behavior is, and that thing is then our oblique asymptote. So y equals.
Will there ever be a situation where that will be
Nope. Not in determining asymptotes, no. So I mean, usually I don't even write it back up here because I just know it's not important. So I'll just kind of do that, and that's my asymptote. Okay, it's okay with everybody. So now the question is, if that's my asymptote, do we ever cross it? Okay, well, if I'm going to cross my asymptote, the thing is, I want to take my original rational function, and I ask the question, does it ever equal x squared minus x plus 1? Does that make sense? Okay, now that is a very nasty looking equation, but we have the ability to solve it. Okay, so how would I get rid of the fraction here? Multiply, right?
Point of interruption. Any freshmen who have not received their computers, please meet Mr. Jesko outside of Mr. Wilkerson's room. Again, any freshmen who have not received their computers. Thank you.
So if I multiply both sides by the denominator, that's what I get, right? Okay. Are we capable of distributing over here? Now I'm going to cheat a little bit for you and tell you, actually, let's do it this way. All right, so once you multiply this out, you get x to the fourth plus 3x cubed minus 15x squared plus 16x minus 12. what happens to this x to the fourth? Cancels. 3x cubed? Cancels. Negative 15x squared? Cancels. Now nothing else cancels, right? So if with negative 19x plus 30 equals 16x minus 12. Now, if I'm going to subtract 16x from both sides, so I get negative 35x equals negative 42. Does x end up being 42 divided by 35? Is that 1.2? So because I get an answer here, that tells me I do cross at x equals 1.2, right? Okay, now so here's the thing. I'm crossing the horizontal, or sorry, in this case, the oblique asymptote, okay? That's my rational function is crossing the oblique asymptote. That means my rational function and my oblique asymptote are sharing the same y value. So if I want to find out the exact location, I can either plug that 1.2 into that left-hand side right there, or I can plug it into the right-hand side. Which one would be more convenient? The right-hand side. So I'll plug it into the actual asymptote, and when I do that, it gives you y to be 1.24. So you cross at that location, 1.2, 1.24. Okay? So we've got all the data we need. We've got our oblique asymptote, we got our vertical asymptotes, we got x-intercepts, y-intercepts, and now knowledge of where we cross the oblique asymptote. Now, just to preface this, I'm never going to ask you to do this at this stage, okay, in this course. I might ask you to come up with this information, okay, but graphing it is going to be a little bit more tedious, time-consuming, using more probably test values. Calculus would be a lot more helpful here, okay? Yes?
So x squared minus x plus 1 isn't the equation for the oblique, then?
Yes, that's the equation for the oblique asymptote. Yes, yes. So I'm going to graph all these things. Okay, so our vertical asymptote was at x equals 2, x equals negative 6, and then we had the oblique at was it x squared minus x plus 1. Okay, so all of those things I'm going to color red, make them dotted. Those are my asymptotes. Okay, and you kind of see the different regions that get created when we generate that. Now we also had some x-intercepts, had a lot of them. 3, 0, negative 2, 0, 1, 0, negative 5, 0. With a y-intercept of 0, negative 2.5. And we crossed our oblique asymptote at 1.2, comma 1.24. And that is point F there. I'll just make it an X because that's where we cross. Okay, so we get all this information. Okay, and I'm going to just real quick type in, just so I can graph this stuff a little bit easier for you. And this would be the part that I think is asking a lot of you. All right, so understanding how asymptotes work and how graphs behave around asymptotes. If I take A and start trying to find points around A, if I move to the left, where do those points have to go? Are they going to go up? Because if they go up, I'm either going to have to cross my oblique asymptote again, which is that curve there, okay, which we know we can't do, right? Or I'm going to have to go up and then follow that asymptote. And if I follow that asymptote, the graph is going to do something like this. Let's see if I can trace this. So if I go up and start following that, and then it's going to start bending back eventually, and that's because as eventually when I get wide enough with this, what's going to happen here? What do I violate by doing something like that? I violate the definition of a function, because a function, if it's going to do something like this and bend back around, don't I violate the vertical line test? Okay. So my point G is actually, as it moves, as x moves closer and closer to 2, it's going to have to go down. Does that make sense? And as I move then to the right, G is going to go up and to the right, and it'll start to hug this asymptote, and we'll kind of demonstrate that here. And this is what I think is difficult to end up doing. But if x is bigger than 2, let's see what the graph of this function looks like. It's that curve right there, which does that start then. You can kind of see it kind of, I think there's a little bit of inflection here. And you can start to see that thing that starts to behave much like that parabola does as x gets bigger and bigger. Does that make sense? Okay. And that there, I believe, is really all that we do with this parabola. Okay, because remember, it's what happens when x is really big. When x is pretty small, we don't really care about what the oblique or slant or horizontal asymptote is doing for us. Now what I want to do is I want to see what does this thing do between -6 and +2. That's another region here. We know we're going to cross this oblique asymptote at F, but if, and this is again, a part that I think, just because of our experience so far, would be something that would be kind of a jerk move if I asked you to graph this. But we get that purple curve there. I'll make it blue again. We get that blue curve, okay? And as we move away from, so we got D, B, and C being intercepts, E being a y-intercept. Again, finding out what is happening between D and B, it would be nice to have some calculus to tell us that maximum. To know what's going on between B and C, some calculus would tell us that minimum. Does that make sense? So that's where maybe we take this in the coming course. But going left of D, we hit this asymptote, right? Or get close to this asymptote. So maybe a test point of like negative, 5.7 or something would help me find a y value down here. So then I know that this thing is going to move that direction. Okay. As I get close to this asymptote at 2, does this blue curve approach that asymptote? Yeah. Okay. So it gets kind of messy looking. Let me hide the asymptotes. But that's what your curve looks like, and that's the reason why these two things, these two branches kind of start separating, is because this one here is following that oblique asymptote, and this one here is following a vertical asymptote. Does that make sense, everybody? Okay. And that if we look at something like, let's just go like x minus 3 divided by, let's raise that to the third, divided by, let's say, x. Okay, I get something like that. And now if we did the long division algorithm here with this, we would find out that there is a parabola. I don't know that I can actually do this real quick. Just kind of, obviously I did a little cheating here. If we take this rational function, which the numerator expands to this green one, okay? But I actually go through the long division. This would be the quotient through that long division. Does that make sense? So take x cubed minus 9x squared plus 27x. What's that last term? Minus 27, okay? And divide that by x minus 1, you get this, okay? So graphing my gray curve, my gray rational function, it looks somewhat like it's cubic, but a cubic should have symmetry, correct? Or a fifth degree, an odd degree polynomial should have symmetry. And if I look at where my cursor is, and that kind of be like the breaking point for symmetry, that branch to the right and the branch to the left are not going to land on each other. They're not going to fold on each other. Does that make sense? But if I put in this parabola, which is the asymptote, would you guys agree that that gray function is behaving around that asymptote? Okay. Now, something that we weren't seeing with this graph because of where I was zoomed in, there's actually more of this graph up here. Okay. Because don't we have an asymptote at x equals 1? Put that asymptote in. Okay, so we've got another region here. Would you guys agree that in this region, if I look at the red curve is being bound by the blue asymptote, which is a parabola, and this asymptote, which is a line? That kind of makes sense? So we get overall that red function, we get that structure, okay, because there are kind of these oblique asymptotes that are laying there in the background that the curve is approaching. Again, like I said, calculus will investigate some of this, okay, because there are some tools in calculus of finding maximums, minimums that would make the graphing of that a little bit easier.
We will,
Okay.
and then like you're gonna teach it.
I do not know that, okay, but if